Go. All right, so hello everybody. Welcome to the first Corundum developer meeting for 2022. And Happy New Year to everybody. Hopefully this year will be better than last year. Better than the last couple of years, maybe. We'll see. All right, so let's get the ball rolling on these update slides here. So all right, so I got a couple of things on the agenda today. The first one is I got a couple of status updates, stuff that I've been working on over the last couple of weeks on Corundum, and then we have a talk from Andre. This is a paper that we put together for Cider, and then I think we have a couple different versions of the talk that have been coming together. So this should be interesting. Hopefully we'll be able to provide some feedback to Andre that'll be useful for the talks. So yeah, that'll be something to look forward to in a few minutes here. All right, so let's see. In terms of stuff that I've been working on for Corundum, I did a bunch of driver cleanup work to, let's see, I'll go over that in a slide in a couple of minutes, but to make things a little bit more straightforward and hopefully help out some of the folks at the MLE in terms of what they're doing in terms of extending Corundum and getting it to run on the Zinc devices to hopefully make it a little bit easier to add the platform device support. And also just make things a little bit more straightforward. I also finally got the address space reorganization taken care of over the past couple of weeks. And this one, I mean, it's basically working. I need to go test it on all of the targets to make sure everything works, because the address space reorganization, it's not only, all of the internal registers that are, part of the Corundum core logic, but also the board specific control registers and whatnot. So I need to go through and test everything to make sure basically that I didn't break anything on any of the targets, because, a lot of stuff got updated, and I definitely could have introduced a few bugs. So hopefully that's not the case. I have not been doing too much more work on the shared interface data path, but that's also something that I've been working on. I rebased that on the latest version of the code after the address space reorg. And then, once I get this stuff pushed back into the core repository, then we're going to be building some more stuff on top of that. And then I've got, the previous couple of to-do items, the variable length descriptor support, the PHY control and status registers, and the 10G and 25G switching. Excuse me. Those are basically the main things that are going to be, up next after these current to-do items are squared away. All right. So moving on to the driver cleanup. This is kind of a kitchen sink of various, minor updates that were made to the driver. Well, some of these are a little bit more major. So I removed a bunch of unnecessary parameters to a bunch of the internal init calls and whatnot. I rewrote the interrupt handling to use the atomic notifier chain in the Linux kernel instead of some of these. I had like this ad hoc for loop thing, which probably wasn't very performant, but the atomic notifier thing is going to be a lot more flexible. So that's all squared away. In a lot of cases, I was passing around indices instead of structure pointers. So I switched that up to pass around structure pointers. So that means that it doesn't make, so the idea behind that is when you have multiple net devices on one interface, then you can pass, a subset of queues to one of the net devices, and they'll be able to figure out, which queues those are based on the indices that are in the structures. So they'll have their own zero-based list that corresponds to, a subset of the queues. So that will hopefully allow that type of feature to be implemented. I also split the buffer allocation from the ring creation, which will make it a lot easier to resize the descriptor rings, basically. And it also means that the descriptor rings aren't actually allocated until you're ready to actually do something with the ring or create the net device anyway. So the idea is that the interface module will own the shared state for the queues themselves, but the ring buffer that'll be created by the net device once you're actually going to do something with it. So this will hopefully help when you have multiple net devices. And hopefully this will also be able to reduce the memory consumption if you're not using all of the transmit queues, for example. So the other thing I did is I split the interface from the net device. So this allows you to have multiple net devices on one interface. And it, kind of peel apart the initialization logic to make things a little bit more straightforward. Again, this will hopefully help the MLE folks who wanted to do something where you had a couple of net devices on one interface to save resources, which I think is a pretty interesting idea, and I'll probably be making some additional modifications to the register space to make doing that sort of thing a little bit easier. And then the other thing that I did that was on the slide that I showed the last time is I split off the common probe and remove logic in the mqnix main.c, and this is partially to help improve or to make it easier to implement platform device support, because we have the PCIe probe logic and we have the common probe logic, and then you can just add the probe logic that's specific for the platform devices. But it also helps with the error handling, because now you can bail out a little bit more easily from the common probing separately from the PCIe probing. So a little bit of an overhaul. Oh, I also did a similar modification to the user space tools as well, in terms of separating out some of the more specific functionality into separate functions. A little bit of a minor refactoring. So this is all done. This is all committed. This is all up on the main source tree on the Corundum GitHub repository. All right, so the next thing that I was working on is the register space reorganization. The idea is pretty simple, to use basically PCI Express style configuration space blocks, where you have a small header on each block that indicates the type of that block, the version of that block, and then a pointer to the next block, basically. And as a result, the offsets are not important, because as long as you start in that defined spot, at the beginning of the bar, then you can just follow this linked list all the way down through all the blocks. And this makes it very easy for software to enumerate everything that's on the hardware, and that allows you to move things around as necessary when you're implementing new features and whatnot. And with this setup, the blocks either can contain registers directly if you have a component that just has a couple of control registers, or it can point to a separate set of registers for things like the queue managers, where you have a very large section of address space that's devoted to all the queue state and whatnot. So this means that you don't necessarily have to pay the alignment penalty of having that header when you have a large number of registers, because you can just separate the two. The other thing that you can do with the blocks as well is you can have kind of a hierarchy. So you can have one linked list at the root, and then this can point to each interface, which will then have its own list. And then on each interface, for each port or for each scheduler, you can have another list. So you can form a nice hierarchy going down the stack to keep things a little bit more organized. And the other thing that we can do with the blocks is we can support fine-grained versioning. So this means that breaking changes are a lot less of a problem. If you make a breaking change, you change some registers, you move some stuff around, you add a new block type or whatever, you can bump some of the block versions. And when the driver attempts to connect to the card, it'll check all the versions. And if there's a version mismatch, then it won't try to communicate with that block. And then the driver can handle that appropriately. It's like, oops, we couldn't find this particular scheduler block or this particular interface control block or whatever. And then you can deal with that either by supporting multiple versions, or by simply bailing out and saying, oops, we have a firmware version mismatch, you need to use the correct version of the driver. And the other thing, I think I've only implemented this in the user space tools for now, but I can also implement this in the driver, is that if there is a mismatch in, say, one of the NIC interface related blocks, we can just skip setting up the interfaces back out of that, but then still register like the dev entry so that the firmware update tool can work. So you can actually flash the card with the proper version of the firmware that the driver can talk to. And this reorganization is going to make it much easier to add or customize, components in the design, because you can very easily add new customized functionality or modify the existing registers. And by changing the IDs or bumping the versions, then you can make sure that you're not going to be performing any unsafe operations. So the initial version of this is done, works in simulation. I've tested it on a few cards. I need to test it on all the boards, and then I'll push that to the main repository. So so yeah, if you're working on a port, then you'll probably have to do some copy and paste work basically to bring it up to date with some of these modifications. I guess one block I can talk a little bit about specifically, most of it has basically just been, it's exactly the same as the current registers, but I've attached a little header on it. The main one that I've made some modifications to is the firmware ID information. I changed the version numbers. Previously, it was just like x.y, right? You got a major and a minor. I changed them to have 4 parts. So it's just, 4 bytes. Each one is one part of the version number. So this will give, a lot more flexibility going forward, as opposed to just, major and minor. And I added a build date and git commit hash. So when you load the driver, it'll actually print that out. And the config.tcl scripts have all been updated to run git and extract the commit and tag information, which are used to set the version number and the git commit hash. So right now I don't have any tags, so the version number is not actually going to be updated. But eventually, once we start doing releases, then the config.tcl scripts will automatically propagate that information when you build the code. Alex, into these configuration registers. What?
One quick comment over there.
Sure.
Folks that care about reproducible builds sometimes frown upon adding the build date and commit hash if there isn't any mechanism for you to add an artificial one. Is just to make sure that you can actually rebuild whatever you did at a different date, for instance.
Okay, so if you want to force a specific...
Exactly, like silly details, but build reproducibility, it really goes a long way. So, and this kind of thing
right,
works.
yeah. Okay, that's
tiny,
a good
tiny,
thought.
tiny,
yeah, I mean, so I guess the other thing about build reproducibility is, how well Vivado handles that. I guess ostensibly... Yeah, I was going to say ostensibly it does a reasonably good job, but I think we've run into issues where there's some chaos introduced in there somewhere, intentionally or unintentionally. So that's a good thought. Yeah. As it stands right now, I don't really have a mechanism for that, but it would be pretty straightforward to add something to the TCL scripts. And that's actually something I was thinking about. I know some folks in China don't necessarily have good access to GitHub because of the Great Firewall of China. So they've been downloading like the archive version, which is just a snapshot of the master branch. So from that, you won't have a git hash and you won't have any tags. So if you wanted to, have a version number or something that's independent of, the git information, I think that would be useful. So that's something that I need to do some thinking about, is where that would live in the repository and how the TCL scripts would locate that and use that to set the version number. But potentially something like that could also be used to override the git hash and the build date. Probably the build date's the most important one, because I'm assuming if you want to do reproducible builds, you're also going to have the same git hash. But I could definitely see overriding the date. I guess a simple thing that we could do is to extract the commit date and use that instead of the build date, basically. Maybe we can have an option for that somewhere, because that would make it reproducible if you're extracting both of those from the commit information.
I don't know if there's any trick to extract that from a git tag. if you're really building off the tree, I don't know how this is done. I can take a look at how people go around this thing.
Yeah, I think extracting it's not too hard. It's just there'll be some command from Git to fetch the the most recent tag or the most recent commit. I mean, that's what I do right now. It's git describe is what you use to get the commit hash. I would assume there's a similar way to get the time. And if you have to do some additional hoops, then you have to jump through in TCL to parse that. That's a different story. But I don't think that's going to be a major issue. We can do some poking around. It's more. I think the implementation is not going to be that big of a deal. It's more just figuring out exactly what's going to make the most sense there. But yeah, that's definitely a concern. But I think that shouldn't be that big of a deal to work around that. We'll just have to come up with a sensible plan. All right, so that about rounds it out for the register space reorganization. And then the next thing that'll be back up is the shared interface data path. I haven't done too much work on this, but I have been doing some thinking about this. As in the initial implementation of this, I threw out the port module because I pulled all the data path components, or everything that was in the port module is now either in the interface module or it got bumped up all the way into the core module. But I think from the standpoint of this new register space setup, I may want to go back and add another port module just to handle port specific control registers for, let's see, what were the registers that I needed to add? So two main things. I think one of them is RSS control, because we want to do that on a per port basis. You might want to use different RSS settings, or you might want to offset so you can get different queues for each one of the ports. And then the other one was, we need some registers potentially for when PFC is implemented to map, the internal priority levels onto the actual output, the implemented priority levels in the output FIFOs. So we need a few registers to do that need to be associated with the ports. Okay, so it makes sense, I think, to have port data structures or these little register blocks for the ports, and I think bringing back the port module and perhaps having a set of those in the interface to implement that would make sense, or maybe even putting it up higher depending on what those control registers need to be connected to. Maybe it makes sense to put it all the way up in core alongside the interface, and then wrap the FIFOs or whatever. So yeah, I might change that, but at this point, at least now that I have all this versioning implemented, it makes it relatively simple to, I could just bump the version numbers, and then we don't have to worry about, backwards compatibility, because the driver will refuse to talk to the newer version, or, vice versa. Right. So anyway, the idea behind the shared interface data path is to, reduce resource consumption when you have multiple ports sitting on one interface. And I think this is going to be useful for a number of different reasons going forward. So I definitely want to, make sure that this works well. I have a couple slides with some more details on this, which, people have questions, I can circle back to that. This has just been exactly what I showed previously in other presentations. All right, so once that's done, then the next big thing on my to-do list is the variable length descriptor support, such that we can improve the utilization of the PCIe bus, and also support more complex operations and properly implement scatter gather. And then I have kind of two other to-do items: the PHY control and status registers, and the switching between 10G and 25G. Which is done at the the PHY level, at the transceiver level. So yeah, these are to-do items for later, once some of this stuff is squared away. And then I've been putting this up more because I've had people asking about versioned releases and stable releases and whatnot. So this is kind of the checklist. Once we have all these things checked off, then I'm probably going to be starting to add some version number tags and whatnot. So application section, that's all done and integrated. Well, I guess it's done on the on the hardware side, but I think there is still a few little odds and ends that need to be done on the driver. But on the FPGA side, that's done. The register space reorganization, that's basically done at this point. Need to test it, and then that'll go into the main repository. Shared interface data path, working well for a single port. With multiple ports, there's still some stuff that needs to be done, but that'll be squared away relatively soon. And then we got to do self-contained checksum offloading, so I can remove the checksum field from the descriptor, variable length descriptor support, and then the on FPGA management core. And then at that point, I think we're going to be in a good enough position to start, adding version numbers and having, proper releases. So that's kind of the idea. We got a couple more things checked off, right? Register space reorganization, that's done. Yeah, so the ultimate goal here is to stabilize the hardware and driver interface. And so that's the idea. All right, so does anybody have any questions on the status updates so far? No? Anybody else have anything, status related to report? I know a couple people were working on things, but I'm not sure if they've joined us today.
I can talk about some stuff. I've been working on improving the receive side. And so I tried to modify the driver to add page pools. So I think it comes in Linux like 5.15 or something. And I was getting up to like 25, 30 gigabits. But now with the page pool, I can go up to like 65 gigabits without maxing out the CPUs.
Nice. Yeah. Definitely like to hear about that.
Yeah. So I'll probably see if I can send a pull request for that. And
well, that's a very, very good improvement. I know there's definitely a lot that needs to be done on the receive side to improve it. So if that's something you've been working on, that's great. Do you have any slides or anything, or you just?
No, actually, I don't have any. Yeah, just an announcement, I guess. Fine. So maybe for next time, I might prepare a few slides.
Sure.
Talk about how it works. I guess another thing. What else? Related to that, I'm trying to get really high speed data in, right? I have a network tab, so I'm trying to read the data in. So what happens is when I first start the driver, it actually ends up filling out all the queues, and then I don't really get anything out if I bring the interface while there's data flowing in. So
okay, yeah. So this is there is an issue on the receive. I'm not sure. I've not done enough work to get to the bottom of exactly what's going on here. But yeah, this is definitely something I've noticed as well. If you bring up the interface when there's data coming in, queues will get stuck. And I've not figured out exactly what's going on there. Obviously, resetting everything with the interface, or with no data flowing, allows it to work. So I'm not sure if it's like a driver initialization sequence problem where things are being set up in the wrong order, and as a result, something's getting stuck, or if something else is going on, if it's some sort of a hardware problem. I'm not sure. So yeah, I would definitely like to get to the bottom of that at some point.
Okay, so I'll definitely have to get to the bottom of that because my interfaces always are dumping data. So
right. I mean, I guess a relatively simple band-aid would probably be to add some additional hardware, kind of at the MAC level, which will stop the external traffic when the interface is down, so that there's no traffic flowing into the interface, until it's ready for it, and then you turn on the flow of traffic. So that would be a simple thing to do. In my mind, a little bit of a band-aid kind of solution, but it would probably work, right? Because then from the standpoint of the data path, you don't have any data coming in. So
yeah, that's not a bad idea. I might see if I can implement something like that. Okay, here's another crazy idea I had, but I'm not sure if something like this is doable or not, would I be able to use one interface? You know how it has a receive and a transmit? Can I use both of them for receiving? So I built a hand-made SFP, right? So I would plug the receive side from two SFPs into the SFP on a board, and then do some rewiring on the FPGA, I guess. And would it be possible to actually use one SFP to get 2 receive fibers
No,
or whatever.
unfortunately, that's not possible because the high-speed connections there are going into dedicated logic on the FPGA, and that's specific to send and receive. So the transmit side, it sends; the receive side, it receives. So if you're only interested in receive, then you basically just have to burn the send side and ignore it. So
Okay.
if you need more throughput, you basically just have to use more transceiver channels. You can't suddenly turn the transmit side into the receive side, unfortunately. So,
but wouldn't it be possible though to wire two RXs to a single physical SFP?
Yes, that was my idea. But if there's a dedicated block for transmit on the
which wouldn't
FPGA,
be connected to any pinouts.
Well, right. So, okay. So, I mean, now you're talking about modifying the board, and I mean, yeah, I guess you could do that, but you'd be spinning your own board. You'd whack an FPGA on there. You'd whack the transceiver modules down there. Once you're doing all that, okay, just whack down twice as many sites, where you can plug in twice as many modules, and then but that's a lot more complicated than just doing something with an existing FPGA board, or perhaps using a slightly different FPGA board. I mean, I guess in your case, you're trying to do some sort of packet capture, right? So you have
exactly
interfaces where you're bringing data in. Are you going to be doing filtering on the FPGA, or are you trying to kick all that data over to the host?
Actually, I'm trying to do traffic accounting. So I'm trying to do per flow accounting to find out which flow has how much traffic. And
okay,
right now I'm just passing.
Right. So you're not sending all of the actual traffic over to the host, right? Because if you were trying to do that, PCI Express would limit you to like 128 gigabits a second, right? So.
Yeah, exactly. So, I mean, one thing I tried doing is like cutting the packets short and then sending just short packets to the host. And I'm not sure if that's going to help out or not, but my FPGA knowledge is limited. My Verilog knowledge is pretty limited. So
right. So I guess shortening packets would work, but the problem is that all the overheads on the network stack are pretty much per packet overheads. So yeah, you can give the host a million really small packets. It's not going to be happy about it in terms of performance. So now, if you're not going to the Linux kernel, if you're going to some custom piece of software, that's potentially a different story. I have heard of some people working with Corundum trying to do some sort of coalescing basically on the receive side, where instead of passing all the individual packets, they're merged together into a larger block of several packets, and then that gets sent as a single packet through the data path and whatnot.
We did that using a switch, by the way.
Right. But then obviously you need to peel it apart again, in the software, wherever that is. So that's certainly an option. Yeah, so if you want to get even more connections in there, well, so you were using a board that already has, I think, 4 QSFPs on it, right?
Yes. We're using the XUP P3R. The bit where it has 4.
And you're using those as 100 gig links or 10 gig or 25?
100 gig links. 100 gig links.
Okay.
But
okay, yeah. No, I was just trying to think if there's you could do more on that board, but I think that board is kind of limited to about 400 gigs worth of bandwidth because it's got those 4 transceiver sites. If you want even more bandwidth, I guess ideally you would get a board with more inputs, basically, which I know they exist. Either you can get a board, with more QSFPs on it, or you can get a board that has some, expansion connectors on there, and then you can feed in more QSFPs that way. But at some point, maybe it makes sense just to get, 2 or 3 FPGA boards.
Yeah, exactly. True.
Yeah, it's like, does it really have to be on one, Yeah, if we're talking about modifying the board, 25 gig, you don't want to be, cutting traces and doing stuff like that by hand. It's from a signal integrity perspective, it's not going to work. So if you're going to make that kind of a modification, you want to make a custom board. And, I don't know if that's in your budget.
Probably not. Not at all. No, not at all. anyway, that's the updates from me.
Interesting stuff to think about. Yeah, it sounds really good, that page pool setup. I think I took a brief look at that. I couldn't figure out if it had much utility outside of XDP. It seems like it was built for XDP, but I guess it also works for just general normal internet receive. So
yeah, it's correct. You can use it without doing XDP as well. What happens is, like, for each packet you get off of PCIe, you allocate a new page, and then that gets passed up the network stack in Linux, and then eventually freed out. So each allocation of memory takes some time. So if you can just take those pages, put them back in a pool, and take them from the pool.
Right. Yeah. So I guess there's two aspects to that. One of them is the page pool, which I think is specifically useful for XDP because XDP tends to circulate pages inside of the driver, right? The page will be handed off to XDP. XDP will, potentially just resend that packet or something, and the page will stay inside the driver. But the next level to that is the page recycling, I guess, where you screw around with the page reference counts, you let the network stack do something with the page, and then it'll free it, and then you can recycle the page again for transmit. I think that the Mellanox NIC does something even more fun. Maybe it wasn't the Mellanox NIC. I've seen some NICs will reuse pages twice for MTU less than 2K because you can put two packets in one page. Right, so you can put one packet in the lower half, and then you can flip and put another packet in the upper half, so you can use the page twice before you reuse it again. So I don't know how much of a benefit that gives you over just eliminating all of the calls into the memory management subsystem in the first place by using the page pool, but definitely there's going to be a performance improvement there. So yeah, unfortunately, my expertise does not lie in, the memory management subsystem in the kernel. So as much as I would like to have some of this stuff implemented, I can't do it myself. I need somebody who's more familiar with how the Linux kernel handles this stuff internally. So if this is something you have working, I mean, that's great. I definitely like to see if we can get that merged in upstream.
Yeah. Okay. I'll try it. Hopefully we can.
Yeah. Sounds good. All right. Anybody else have any comments or anything, or shall we turn it over to Andre? Nope. All right, Andre, are you ready to go?
Yeah.
You're good? All right. Well, okay. Take it away, Andre.
Yeah, thank you so much. Okay, so this will be a short presentation on our paper, the DRDMA, bringing zero-copy RDMA to database systems. So just to jump right in, right? So I assume most people here are familiar with RDMA. So how it works, or in theory, is that you just have your networking card. You point your networking card to regions of memory, and then the content of those regions gets transmitted, right? And if you doing it right, then the performance should be very good, right? You should be able to take full advantage of whatever throughput your network offers. So, but in database systems, we often have very small values. So as soon as the values get small, you add a lot of overhead, and RDMA, the performance drops significantly. And in that case, there's very little that the card can do to get better performance. So what then most database systems do when they use RDMA is they simply kind of have all this gathered data. They copy it into a contiguous region, and then they point the networking card to that region, and then they get, again, very good performance, right? But now they spend a lot of time, the CPU has to load all the data into its caches, copy it, and then put it back out. And so what we're arguing is that in database systems, the previous picture was actually wrong, because the data is not just arbitrarily shuffled in the memory. Instead, it's it is very structured, and most pieces of data are in close proximity. However, RDMA in its current form cannot take advantage of that structure and that proximity. So what we're proposing is DRDMA that should be able to take advantage of that and then give you good performance in these cases. Okay, so the outline of the talk, I will show first a few DMA and RDMA micro benchmarks just to show you how bad the problem is. Then normally we'll talk about abstractions, but because I don't want to take up too much of your time, we're going to skip over that and go straight to the hardware stuff, the architecture. Okay, so I don't want to get too much into the database stuff, but basically if you have a database system with multiple servers, you from time to time, they have to exchange data. So this is your database table, and basically those are integers in arrays, right? And so then what the programmer would kind of do is would create these work requests that point to the data, and then the card would fetch this data and spit out packets. And what was kind of surprising to us is that even though all those integers and this data is like right next to it, next to each other, right? It's in contiguous memory. You still get like the card, like commercial cards, like the Mellanox Connect X5. It will still, like for each number, it will issue its own PCIe read, which obviously is very inefficient because those are like 4-bit integers, right? So actually, like each of those SGEs is at least one pointer and a length. So you have to send more control data to the card than you actually that the card itself will be able to fetch, right? So it'd be better to just send the data in the first place. So, and that's what database systems do, right? They just kind of take all the rows that to go to one server, put it into a transmission buffer, have one work request, and then send everything in one go. And we did some experiments here, and it turns out that, so first of all, the zero copy that I showed before is like extremely bad, right? You have like 50% of a CPU and get like one gigabit per second or 2. And the copy out is better, but still now we use like one full CPU core to go to 23 gigabits per second, right? So, or 18 gigabits per second. So to like use the full bandwidth, you have to sacrifice 5 cores of your CPU to just copying data. So why is it this bad? We did some micro benchmarks of DMA reads. So you see, like with increasing size of the reads, you get better performance, and actually the reads have to be quite big to like get any decent performance, right? To get all of it, you have to read at least 256 bytes. What's also super surprising is that it's actually not only when you do a 8-byte instead of a 2-byte transfer, not only you get like 4 times more data, but actually it is faster to read 8 bytes than it is to read 2 bytes. So we kind of did some more benchmarks to figure out why that is, and it turns out it happens if you hit the same cache line. Like if you look at, so here again we have the number of bytes that we have in one transfer, but this time instead of kind of reading contiguously one byte after another, we have gaps. So for example, if we read 2 bytes and then we have a stride size of let's say 64 bytes, then each time we read 2 bytes and then we skip 62 bytes. And what happens is that you see that this 64 actually is kind of a magic number, that as soon as we hit that offset, that there's no performance improvements anymore, right? And 64 bytes is the cache line size. So we assume that is mostly like hitting the same cache line repeatedly leads to this higher latency and even worse throughput. And when you have these in database systems, these integers that are this close together, that's exactly what is the case, right? Is that they're probably gonna lie on the same cache line. Okay, so then, as I said, I will skip the abstraction and kind of go straight to the hardware part. So what we're kind of proposing with DRDMA is that we have higher level abstractions that then allow the NIC to reason about what data to fetch and optimize the schedule of that. So there are kind of similar components that you would find in a normal NIC, is in that you have a DMA engine that fetches the data from the host, and you have a packetizer that actually turns this stuff into packets. But then we need some new components because our NIC needs to be smarter. So we first have an optimizer that takes in this high-level abstraction from the programmer and figures out how to fetch that data. It then sends those, we call them bounding boxes, to the DMA engine that fetches them. And at the same time, it tells the assembler where the data will end up. So once the DMA engine fetches the data, it will put it into segmented memory and then give the assembler a completion that then knows where the data is and then can assemble a packet or the payload of a packet that is then sent to the packetizer. So how does the optimizer work? So let's say we have a description here of the data, and there are gaps in here, right? As we saw before, like commercial NIC or RDMA NIC would kind of just for each one of those, it would just like issue one DMA read. Now the optimizer in our case can kind of try to think about and reasoning about, well, what would be a better schedule? So it could either like just like eat this gap and still have like two DMA reads, or it could eat this gaps and leave that one alone, or it could even like just fetch the whole thing, right? So once then the optimizer figured out which of those plans it wants to go for, it sends that to the DMA engine. Once the DMA engine fetches the data, then puts it into the segmented memory, right? And here the gaps here we see are the C1 and the C2, which would be columns in a database. So then once we get the completion, the assembler then takes the data out of the segmented memory, and it does this with a crossbar. So we have this programmable crossbar where in each cycle, some rows will be passed on to the packet payload buffer, which is down here. So in the first pass, it would kind of just fetch those three rows or like segments in the memory, and then send that to the packetizer, which then outputs a packet. And then in the next cycle, it would kind of try, or like just in the, doesn't have to be like a physical cycle, right? But just in the, yeah, the next time there's space in the pipeline, you'll then fetch those three segments and output those to the network. So we did some micro benchmarks to see kind of just like how many segments do we have to read per cycle to just see how feasible it is to design such a card. And turns out you only like a few more than 8 segments per cycle to like read line speed with when you output RDMA packets. So in that case, we had 128 bytes payload, and the RDMA headers are 72 bytes. So it's like roughly 200 byte packets.
And how much are you reading out of each segment, and what clock frequency?
So the clock frequency is the same as the CMAC, right? So it's 322 megahertz, and the segments are 4 bytes, right? So the running example with the table has 4 byte values in each column. Okay, so then what is our research agenda? So there's like still a lot of open question on how to actually design the optimizer. So one thing we could do is kind of see, we saw that if you have like if you only have very small reads, then that's very bad, but it's still somewhat of an open question. It's like, can you still tolerate a few smaller reads when you have a lot of large reads? Then where do we actually implement the optimizer? Should it be in the driver, also in software, or do we actually do it in hardware? And then depending maybe also on that is what kind of algorithm do we use? As there's certainly with dynamic programming, you can kind of get an optimal schedule, but then maybe there's like a faster algorithm that is still reasonably good that kind of uses a greedy or an approximate approach. Then payload management, like how many segments do we need in hardware so that we can read from those 8 or more segments each cycle, and how do we kind of spread the data over those segments to assure that that is the case. And then also how do we design the crossbar, or how actually is going to be implemented. And so for a conclusion, so with the advent, so already with 10 gigabits, with 100 gigabit networks, we already saw that we need like 5 CPU cores, and in the future it will get worse, right? We'll go to 400 gigabits, 800 is in the works, and there's even talk about specifying 1.2 terabytes per second. And with those speeds, copy out is simply not viable anymore. With DRDMA, we replaced the imperative with a declarative way to describe the data. So I haven't talked too much about this, but basically we want to break this dogma about that basically with RDMA, you give low-level instructions to that networking card on how it should fetch the data, right? And there's very, very little leeway, and we kind of want to break this dogma and give the NIC make them more powerful and smarter so that it can come up with its own DMA schedule. And so with that, we then move the transfer responsibility to the NIC, and hopefully in the process, we free up CPU and memory bandwidth to the database. And that's basically what we're working on now, right? Is to get to a full implementation of this. And I guess that's it. So thanks, and if you have any questions, let me know.
All right, well, that was a great talk. Do we have any questions for Andre?
Yeah, I guess I'll ask a question. Like, when there's multiple like reads being issued, are they like issued all together, or are they like independent requests and then the optimizer joins the results and sends them back? So let's say I'm writing a database, I'm trying to access somewhere else with RDMA. Would I have to write the request in such a way to know how it would get optimized on the other side? Does that make sense?
So I'm not sure, like, so we have a different abstraction, right, where you kind of then express how the data is structured in a more declarative way. So yeah, you have to change how you transmit the data, but then the optimizer should be able to figure out like how to fetch the data, right? So
this is an abstraction to use on the database side, right? And on the wire, you wouldn't know that the DMA were optimized on the database side. So the thing is, the database gets these requests to traverse data and send data on the network. And invariably, when it gets the time to send the data on the network, the data is all scattered. So the opportunity here is, instead of describing exactly where each of the pieces that need to be transmitted with a large control information or large work requests from our DMA, we can kind of use patterns. We can say, oh, my data is scattered around, but it's in a pattern. You know, the gaps in my data happen very regularly. So we have very compact ways of describing a lot of data at the same time. And then the NIC is free to do a DMA schedule. Now, sometimes we have operations like a database shuffle, right? When you have like parallel, like very, very heavy analytics, and you have several servers working at the same time on the data, they happen to exchange data a lot. So one operation is basically a data shuffle. A data shuffle in database is you take one row, send to a server, the next row is going to go to another server, the next one is going to get to another server, right? So from a network perspective, this is super fragmented, right? But then we're trying to implement ways in which you don't declare, oh, I want this to go to the server, that to go to the server. You declare, I want to do a shuffle. And in a shuffle, the card would know, well, there's no point in fetching just one row because I'm going to transmit the next row and the next row as well. I'm just going to transmit it to different QPs. So there are situations where you can bring like a ton of data at the same time and then figure out on the card how you're going to distribute, right? You basically bring it on the card and you immediately feed it to different queues. Something aching like that. That's what the segmented memory is trying to do as well.
Okay, I see. And then do you need a good abstraction then to define or declare what you're trying to fetch, right? So I think that's probably also a pretty big research challenge, I imagine.
Yeah. We have some primitives, right, that we think can capture a lot of cases. But then, like in every system, there will be stuff that you cannot express with those, right? So the goal would kind of be to like keep it extensible, and then maybe, I mean, yeah, it's an open research question, right? Maybe there's like a set of abstraction that can kind of cover 99% of all of the cases, and maybe everybody should have their own ones, right? So we would just kind of impose some like constraints on what you can do, right? So certainly like the optimizer needs to be able to reason about where the gaps are so that it can kind of like actually optimize anything, right? And it kind of needs to be repetitive or like it just needs some patterns, right? Otherwise there you're just using RDMA.
It almost sounds like there's a need for something like P4 for DMA, where you sort of have a a virtual machine, if you will, that sits in the DMA engine that can perform some of these operations. Although I guess the flip side is if you're doing your optimizer, how the description is fed into the optimizer and how the optimizer handles it is probably the most important component of this.
You touch a very good point there, because we think we can teach the optimizer to optimize independently of the way you describe the structures if you invert the problem. So if you create a new way to describe your data, the optimizer needs to be able to ask your structure what we're calling like gap analysis questions, right? So the optimizer is going to ask your data structure, your way to describe the data is like, where are the gaps? Do the gaps occur in a succession? In how many, if I use gaps to divide the data, how many stretches of data do I have, right? And so implementing a new way to describe your data should come with routines that the optimizer could call and say, okay, tell me, answer these questions, and I'll answer how you should merge or not the different gaps. So we'd like it to be extensible this way. And by the way, this is a great like use case for the application block in Corundum, and this is why what this whole thing get together, right? So we kind of move the DMA responsibility to the application block, and if we change only slightly the segmented memory, we hope to be, if not fully, like very, very closely compatible with Corundum. Just lay our logic on top of it on the application block. But yeah, these are good questions. The big thing is also is in software we can do pretty sophisticated scheduling, but then you're eating away a little bit at the latency that you're going to get, right? Throughput's going to be amazing. The DMA is going to be as good as you could possibly get given your gap configuration. But then so we need to study those algorithms a little bit as well.
Okay, well, it looks like really interesting work, though. I'm impressed.
We're excited about it. Yeah. And it's kind of our sort of excuse as well. We're super interested in participating on pulling out the DMA, right? Because the RDMA implementation over Corundum, because it makes total sense for us to understand very well how this is done and potentially, maybe do some of these things ourselves. So super aligned with the agenda of this group, we hope.
Yeah, I mean, I guess Corundum doesn't support RDMA right now, but we can certainly think about, how to do some more fancy stuff. And then eventually, once we get some of the RDMA stuff actually working, we can hopefully fit the pieces together. So, but yeah, definitely having a use case for, handling some of the RDMA operations from inside of the application section, I think is important to think about architecturally, and how that would fit into, the core data path for handling, the normal RDMA operations. So not sure how that's going to work at this point, but I mean, that's the point of this type of research, is to kind of start getting your head wrapped around what all the pieces are and how they need to fit together. So you're saying that's kind of the point of CIDR to some extent, is having some of this, almost pie in the sky kind of stuff, not necessarily, you don't have the complete design totally figured out, but it's like, hey, this sounds like a good idea. Let's see if we can make it work. Done some micro benchmarks. It looks useful, but we got to hammer out the details. So
right, yeah. The CIDR is we have a problem, and we think that copy out really is not gonna copy out. And then the questions that we're having is sometimes people say, oh, databases are not gonna need 400G. But the thing is, there's sort of every other year, we see an engine that could do, the last generation of engines that we've seen, it could do 150, 200 million of operations per second in current machines, right? And these papers get published without networking. So you're kind of generating the transactions internally as if magically, the transactions were delivered, right? And the database performs the queries. And these are like TPCC, these are not key value. These are actually queries, like using indices and sometimes doing joins, this kind of thing. So sometimes the pushback that we get is, who's going to need 400G? But then the same question was like, who's going to need 100G until someone performs 150 million operations a second? That's 100G right there with the smallest packet amount, like you would have 148 million packets. So the CIDR is like, okay, we're going to have a problem. We're going to have a problem down the road, and this down the road could be relatively soon. I have 400G equipment in the lab right now, and there's no point. Like, what are you going to do? Are you going to take 20 CPUs to do copy out? You're not, right? Condemn half of your machine.
Well, so I guess what you got to do is start doing this on the GPU, right? Do you get thousands of cores?
There is the GPU folks. They do work, and there's amazing knowledge in the database community about how to push things to the GPU. In the GPU, they're not about volume of transactions. They're more analytics. It's like when you do have heavy stuff to be calculated, there's a little bit of penalty moving things to the CPU. So you don't want to move like small little transactions. You want to move one heavy one, right? So, but when you are in this situation, which is very common in analytic databases, yeah, GPUs are amazing as well. And by the way, you can issue RDMA from GPUs these days. So it's kind of interesting.
Well, I guess now we're having more of the DPU type devices, data processing units, where it's kind of a combination of a GPU and a SmartNIC sort of setup. I'm sure those are going to be big in the database space soon, if they aren't already.
There's a startup, it's called Fungible, that has something like that. I don't know, Mellanox brands some of their cards like that, but Mellanox is doing bump in the wire in different configurations, right? And we think the solution is deep integration. This kind of, it's not SmartNIC, I'll leave you some cores here or some FPGA logic for you to run. This is very, very different from the philosophy of the application block. The application blocks, basically, you have those tentacles, those wires, like in several stages of your card that you can basically flip. No, now the control is going to go over there. It's going to be on the application block rather than the regular control on the card. So we think this is the solution is there. It's rendering the card. It's not just more active. Again, it's rendering, make the process of pushing data like one and between the card and the application, like be one, not just accelerate and then push it to the card. I don't know if it makes sense, but
that makes sense. Yeah. yeah, you make that interface more expressive, so you can make it more efficient by tailoring it more specifically to the application you have in mind. So
yeah. And we haven't even mentioned this, and it's super early, but coherence will play a role here as well, right? Because maybe part of the data can be already on the card, or faulting the data, bringing the data to the card could be the DMA schedule. You can very well translate that into, let me fault a few cache lines, and let me issue some request some cache lines and bring them together. So technology that's coming also begs this kind of pushing this knowledge to the card. It's going to be, we hope it's going to be easier to do this data transfer.
Right. I guess was the current setup that you're putting together for the paper, that's mainly just queries and reading. But if you're talking about writing into the database, then that definitely opens up, many other issues in terms of, where's the latest data and so on and so forth, and how do you keep stuff current as things are updated?
Yeah, it's too much to bite at once, but yeah,
right.
yeah. If you're writing it, and the writing happens to be on your card as well, the data is already there. But yeah, definitely, there's some people study that a little bit, but again, the technology is coming, and we think we should shake this tree a little bit. There's some notions that need to change, otherwise we're not going to get at high speed without sacrificing a ton of CPU.
And even for that paper, it would be interesting, right, to get coherency, because basically what we assume here is that, or like the programmer has to assure that when he sends out the data, that data is not modified by another process, right? And so as soon as you have coherency, then maybe we could do something where, well, if it comes in the right time, you can still ship out the full transaction, don't have to abort just because at one point, like one integer changed and you have to stop the full transmission just because of that.
All right. Well, that's been a really good discussion on databases and how Corundum will fit in there. Is there anything else that people want to discuss, or is that about rounded out for today? I see the folks at MLE haven't joined us, so I guess nothing new on their end. So, all right. I guess there's nothing else to discuss, then we will reconvene in 2 weeks then, right? All right. And I guess I'm looking forward to hearing about the packet, or the page
pool. Yes,
page pool. Yes, page caches. Yeah. All right. That'll be interesting.
Okay. All right. Thanks a lot. See you in 2 weeks then.
All right. Sounds good.
See you.
Talk to you.
Bye.
Thank you, guys. Thank you.